Very good. Welcome back. And so I didn't get a chance to talk about skin-to-skin contact last time. I'll just mention it really quickly. There's for a bunch of reasons. One of the other things that is critically important after delivery is skin-to-skin contact with the infant. To me, at this point, the research is well established enough that I would say that there is no excuse for anybody to take an infant away from the mother at the moment of birth. Instead, the infant should go immediately on the mother's belly, and then that skin-to-skin contact should not be broken. And then that actually is an incredibly important part of establishing breastfeeding. And I'm getting suspicions that it's part of the the hormonal rebalance of the mother, her body understanding that she's going from pregnancy mode into lactation mode. And that bonding between the infant and the breastfeeding bonding, I also suspect, I don't have hard science on this yet, that some percentage of women who have a hard time beginning lactation after birth, it's because they were not allowed to have that bonding and skin-to-skin time with the infant immediately after birth. So vaginal delivery is ideal if the mother's microbiome is in good shape, and then immediately should go to skin-to-skin contact. Protracted skin-to-skin contact, which again, if the mother's skin microbiome is healthy, will start to inoculate the infant's skin microbiome. Okay, and will also hormonal cascade in the mother's body and will begin the bonding. And what you'll see is if everything is going well, then the infant will orient and move towards breastfeeding and will naturally receive colostrum within the first hour of birth. And that will jumpstart the whole process of lactation. So to me, that's very important, yes.
Would that also be one of the leading causes into postpartum depression is the lack of that contact?
I suspect, I don't have hard evidence, but for a lot of reasons, I suspect that one of the contributing factors to postpartum depression might be the lack of the mother's having that bonding time and the skin-to-skin contact so that her body makes the transition from pregnancy to, the body needs to know, hey, there's like the world's most incredibly chemistry, setup is the mother's body during pregnancy. And now it has to make this shift to I'm no longer carrying, another life inside of me. I now have to support that life outside through lactation, right? And it's a massive set of hormonal changes and everything else. So anything that we could do to support the mother's body in that transition seems like it would be a good idea, doesn't it? Yes.
Is that true with the C-section as well?
Yes.
Okay.
Yeah. I mean, whichever way you deliver the skin contact. For all the dads out there, I think skin-to-skin contact with the father is also important as well. Just immediately after birth, it's the mom that should be first because you need to establish that mother-child bond and the lactation, right, and get the colostrum. But then you should also have the dad have that skin-to-skin contact with the infant. It's part of that familial bonding that goes on there. Okay? I know we could talk about all that for a long time, couldn't we?
Made 2 sessions of microbiome now. We're just not going to do the EMF.
Well, it turns out EMF RF is also really important for health. What's interesting is like my undergraduate degree coming through was electrical engineering, and back when I was coming through school, there was pretty much this idea that the only way that electromagnetic fields, RF and so forth, could hurt you was through thermal damage, right? And what that basically meant is, yeah, if we get a really, really strong signal, it can heat you up, and bad enough, it can burn you, right? And so when you go through and you get, how many of you have your ham radio license? Okay, how many of you remember having to do the RF safety part? You get into RF safety when you go for your general more. It's like, right, when you go for your general, because typically there's not that much RF safety covered in the technician license, but with the general license, it's like, yeah, you have to like be aware that you could get, radiation, thermal radiation burns from radio frequency if you're sending out a 1500 watt signal on your antenna and you get too close, right? Okay. And for a long time, if you tried to suggest that there were any other health implications to electromagnetic fields or RF radiation, you were basically scorned and told that that was just pseudoscience and it was ridiculous and so on and so forth. Well, I would also say that there was a lot of monetary incentive to not know any different, because there are, the electronics industries are huge industries, large amounts of money. And if there were profound health impacts from exposure to these, have profound economic impact, right? And as a result, there is a lot of incentive to not think about these things. But it turns out they are important, and we do need to take care of them. And so, yes, there is more information in the biocompatible design standard about all this. But we're going to start off with the question of what even am electromagnetic fields, or EMFs, right? Electromagnetic fields are forms of radiant energy produced by electric charge, changing electric fields and moving electric currents. Okay, so an electron or proton all by itself creates, if it's not moving, creates an electric field. If it's an electron, it's a negative, what we defined as negative, and if it's a proton, it's what we defined as positive. I say it that way because that was actually just we could have put the positive and negative either which way, right? They're just opposite of each other, and we just happen to call the proton positive and electron negative. Okay, but either one of those creates an electromagnetic field. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Low energy forms are non-ionizing, while the highest energy forms, such as X-rays and gamma rays, are ionizing, meaning they can remove electrons from atoms and damage biological tissue more directly. Okay, so a lot of the stuff we're talking about, the reason that it was considered to be not problematic was because it was non-ionizing radiation, right? Therefore it can't hurt you. It's not blasting electrons off of atoms and things like this. Okay. By the way, this form of the word radiation is different than when we say radiation coming from like uranium or plutonium. Energy. It means it's travels as waves, electromagnetic waves, moves through space that way. Okay.
Similar to the way heat radiates.
Yes. Well, actually, heat radiation is carried by EMFs in the infrared spectrum. Mostly. Okay. Right. Note that for all of you electrical engineers, note EMF can mean either electromagnetic field or what? Electromotive force, right? Depending on the context. In this presentation, when I say EMF, I'm referring to electromagnetic fields, not to electromagnetic motive force, which is the term in electrical engineering related to voltage. So in electrical engineering, when we write Ohm's law, we write it as E equals IR, where E is electromagnetic force in volts, I is current in amps, and R is resistance in ohms. Okay, E equals IR because V is typically used for velocity, and so in order to keep those things from being confused, we use E in electrical engineering for voltage, because that's not confusing at all. Oh, and yeah, the other thing is that in electrical engineering, what's the square root of -1? I? No. There's I's are used for other things, so we call it J in electrical engineering. Right? Yeah? Any other engineers with me on this one? Yeah, we call it J when you're electrical engineering, because that's not confusing either. Okay.
The low energy versus high energy, is that related to frequency of the wave?
Yes. So intrinsically, the high energy waves are higher frequency, shorter wavelength. Okay. And we're going to look at that here in just a second. As a matter of fact.
Hey.
Nope. Not going there. Not going there. Okay. Electric versus magnetic fields. Okay, so when they travel, so when you have moving moving charges, it creates electric and magnetic fields. This is how they're related. The direction of travel, this direction, you can see that the electric field and the magnetic field move at 90-degree angles to each other, propagating through space, right, via the right-hand rule, okay? So an electric field, which we'll call an E field, is the force field, the field of force, created by electric charge or voltage, even when current is not flowing, right? But a magnetic field, which we're going to also call a B field, because electrical engineering, and we have to change all the letters. It's not an M field, it's a B field, okay? Is the force field created when electric charges move, such as when electric current is flowing through a wire or device, okay? So when we talk about electromagnetic fields, it's the combination of the electric field and the magnetic field propagating through space. You're with me so far?
Because they can't do it separately. They
Right.
always do it together.
Yes. When they're moving, they're together. That's why they're called electromagnetic fields. Now, yeah, see if there's anything else I want to say about that. Yeah, we'll keep on going forward. All right. Okay, so then we have the spectrum, right? The electromagnetic spectrum. And this starts up here, we have the wavelength, and down here we have the frequency. And the rule of thumb is that the higher the frequency, the shorter the wavelength. And I'm not going to get it. There's an equation that relates the two. We won't get into that right now because it includes basically the reciprocal relationship with the speed of light in there, right? And so there it goes. But we're going to concentrate, we're just going to use mostly frequency today just to kind of, because that's what it's usually given as. When you say, oh, my Wi-Fi is running at 5 gigahertz, we're in the frequency domain, right? Or I'm tuning my FM radio to 98.3 megahertz, right? So we're in that domain talking about things today, okay? So what you see is down in the really long wavelength, really low frequency range, we have radio waves like AM radio, FM radio, and then we get into these ranges here where you're getting into things like Bluetooth and Wi-Fi and cell phones and so on and so forth, right? Then you get up to where we have microwave ovens. Why is a microwave oven at this frequency? It's the one that resonates with the water molecule, right? So when you throw it in there, it resonates with the water molecule and it actually imparts energy to the water molecules. So what you're literally doing with the microwave oven is you're bombarding it with an EMF field that's really strong, and that's tuned to heat water. That's why a microwave is much better at heating something that has some moisture in it. If you've ever tried heating something that's super dry in a microwave, you're like, why is this not working? It's because it's trying to heat the water, okay? And as we go up, we get into like where there's radar and so forth. We eventually get up to the point where we're into infrared light, which is one of the ways that radiant heat is moved around a lot, then into visible light, and then into ultraviolet. Then we keep on going up. We get into X-rays, where you go to X-ray machines, and then your radioactive elements start to give you like gamma rays and hard X-rays and so forth. Those are ionizing, right? So that's the spectrum. Now, most of the things that are emitted by human technologies are in this range right here in your everyday life, okay? They are either very low frequency because they're coming off of like the 50 or 60 hertz from the power in our building, or they are part of, some technology like these things that, the glowing rectangles that emit, or they're part of your, all the other kinds of electronic devices around your house. They're normally in this range, and those are the ones that we're most concerned about. Hopefully, you don't have an X-ray machine in your bathroom, okay? Or a nice supply of uranium or plutonium under the kitchen sink that you have to worry about. It does turn out that in industrial circumstances you do have these. And as a matter of fact, one of my letters after my name is RSO, Radiation Safety Officer, where you go through and how X-rays and radioactive sources exposure to humans for safety in medical situations and so forth, right? How to measure that and how to keep things safe and so on and so forth. Hopefully, that's a whole different thing. We're not going to talk about that today because it's a very specialized topic, and I have to go back and take a week-long class in that periodically to renew my RSO certification. Okay, so we're not going to talk about that stuff today. But what in the world are we talking about with frequency? Okay, everybody know what a hertz is? 1 hertz? Okay, so 1 hertz simply means 1 cycle per second or 1 vibration per second. It's 1 hertz, that's all it is, okay? Used to measure electromagnetic fields as well as sound. Like right now as we're talking, the sound that's going through the air on the low end, with you hearing me, is, well, about the lowest we can hear is somewhere between 15 and 20 hertz. That's about as low as we can hear. Below that, we can just feel it. But most of the information that you get through the air is coming between, say, 100 to 200 hertz on the low end, okay, up to about 15 kilohertz on the high end. And a younger person whose hearing is excellent might be able to hear up to 20 kilohertz or 20,000 hertz. Okay, that's sound range, and that's just vibrations in the air. Electromagnetic spectrum is a completely different thing because what it is electromagnetic fields. It's not vibrations in the air, it's electromagnetic fields, which means that can propagate through empty space where there's no air. Okay? Is that making sense?
Yes.
Right. Okay, so 1,000 hertz is a kilohertz, 1 million hertz is a megahertz, and 1 billion hertz is a gigahertz. Okay? So if you've heard those terms and you didn't know exactly what they were, 1 gigahertz means that it's actually vibrating 1 billion times in a second. Okay? So 2.5 gigahertz signal means that the electromagnetic field is vibrating that fast. Okay? That got us enough to go forward? Okay. So radio frequency radiation is divided into bands. Okay. This, by the way, is the spectrum chart for the United States. And what I want you to look at is how many holes of unused frequencies do you see? Basically nothing. Okay. Every single bit of that frequency band is given to somebody. It can be everything from unlicensed Wi-Fi to Bluetooth devices to cell phones to marine radio to military radios to satellite transmissions to, everything you can think of that uses some sort of radio frequency communication, your handheld walkie-talkies, all of those have some allocation at some frequency. It's like packed from bottom to top. Okay? Now, radio frequency radiation is the portion of the electromagnetic spectrum used to carry wireless signals through space. It spans extremely low and below infrared light and includes the bands used for radio, television, cellular, Wi-Fi, Bluetooth, radar, etc., etc. Its place in the spectrum matters because frequency affects how signals behave, how much information they can carry, how they interact with materials and biological tissue, and what kind of exposure patterns they create. One of the things is down here in the ELF, which is called extremely low frequency, okay, and super low frequency bands. This is a lot of the frequencies around which noise from electrical circuits in buildings happen, okay? So a lot of cases when we're measuring electric fields and magnetic fields caused in buildings or by power wires and so forth, those are going to be down at the 50, 60 hertz, or they're going to be a harmonic of that. So if it's 50 hertz, then it could be 100 hertz or 200 hertz or 400 hertz. It's harmonics or that sort of stuff. So they're down in that range. So when we start talking about measuring electric fields and magnetic fields and how they might affect us, we talk about those. We're talking about measuring down in those ranges. When we talk about RF measurements, we're going to be talking about the stuff that's up here, typically a few kilohertz and above, that's used for wireless communications. Okay? Is that making sense? Yeah. Okay. Any questions on this? By the way, what does HF stand for? High frequency. What is it used for in ham radio? Worldwide communication, right? And then VHF and UHF, very high frequency and ultra high frequency. These are what you get with your technician license, and that's used for more line of sight communication and so forth. So regional, your handhelds and so forth, right? So that's how those fit in there. But then all the other stuff like television signals and AM, FM radio and everything fit into all these bands as well. And then you get up into these areas in UHF and SHF, right? And you start getting into the stuff that's in 5G phones and so on and so forth. Okay. Health impacts of EMF exposure. So obviously, the one we talked about at the beginning was high exposure causing thermal effects. That is, tissue heating, burns, heat stress, and organ damage at extreme levels. And for a long time, all of the safety levels that were given out by government organizations were based on that, right? So, for example, everybody remember the whole thing about like whether or not cell phones caused problems? A lot of the research they basically did is they took one of these things and they put it up next to your head and they had you talk on it for a while. And guess what they were trying to figure out? Does it heat up your ear and your brain? Right? And if it didn't heat you up, then obviously it's not doing any damage. Ta-da! And so they said, well, yeah, sure, if you hold it up, and it's on the highest power setting and you hold it up there and talk on it for an hour, eventually we can see a little heating. Therefore, maybe don't do that. Maybe. That was their whole approach to safety, okay? Because the industry didn't want any other answer. They weren't really interested in that. Yes?
Was it not that they found it was causing heating? And so basically all the pamphlets, if you actually read through for your iPhone, it's hold it at least an inch away. And like the early buckles held the phone an inch off your...
Yeah. So yeah, they were like, oh, okay, if you're worried about thermal heating, then use speakerphone or whatever, right? And that was kind of what you got. Okay. So how about all the other things? Neurological and cognitive. It can create, so different levels of exposure to these fields can create sleep disruption, headaches, fatigue, changes in attention or memory, reported in some populations, electrophysiological effects like changes in brainwave patterns, neuronal activity under certain exposure conditions. And by the way, these are just the ones I could find peer-reviewed science for, okay? Because when I'm teaching this stuff, I have to make certain that everything I say is defensible, right? But what's interesting is some of the best research isn't coming out of the US, it's coming out of places like the EU, and some of it out of Asia, and actually some of it out of Russia. So interesting stuff, right? Oxidative stresses, right? Endocrine and circadian disruptions, potential disruption of melatonin signaling and circadian rhythms, reproductive and developmental problems, reported effects on sperm quality, fetal development, early life sensitivity. Although the evidence is mixed there, they're still trying to come up with stronger science on that. Cancer risk, long-term, classified as possibly carcinogenic by the International Agency for Research on Cancer. And then there's the whole issue of electromagnetic hypersensitivity, reported symptoms such as headaches, dizziness, and skin sensations with currently unclear causal mechanisms. There are some people who seem to be just more sensitive than others, right? Now, this is still quite controversial in the science. There's some people wanting to say it's all psychosomatic and so forth. But from what I've seen, there seems to be evidence that there are people who are quite hypersensitive. And the exact causal mechanisms for all of that are still not fully understood. So what we're looking at is we are looking at managing our exposure so that we are kept at safe levels. That's what we really want to do. It's like, even if we don't understand completely all of the biochemical processes by which these fields interact with our biology, it's like we know that something is going on, and therefore precautionary principle tells us we should actually manage this exposure below areas where we feel like it could be potentially risky, right? So what we're going to look at and think about is how do we measure that and what do we do? Well, okay, well, what are the top sources of high electric fields? Right? The high electric fields are primarily driven by voltage, especially in close proximity to energized conductors or devices. Create that for us, unshielded or poorly grounded building wiring, especially near walls and ceilings. And the reason is that walls and ceilings are where all of our electrical wires are run inside of, right? So when we measure it, you'll typically find in the middle of the room, down low will be much lower, and we can get close to wall where there's a conductor in the wall, or up close to the ceiling where there's a conductor going through the ceiling, and you might find a much higher field there, okay? Power cords, extension cords, energized cables near the body, lamps and plugged-in devices close to beds or seating areas, electric blankets and heating pads. This really puts it right on top of you. I do not recommend electric blankets or heating pads because they're just putting those fields right there on you. Yes.
What if you're using a DC variant?
Those are better, but they can still produce electric fields. They'll just typically, the magnetic field will typically be much lower. They can produce static electric fields, not AC electric fields, which we'll talk about in a minute. Okay. All right. Appliances with high voltage potential and overhead power lines and nearby electrical distribution infrastructure, outside power lines and so forth can create these fields, okay, electric fields. Right. So these are all things we want to be watching for and thinking about with electric fields. Well, how about magnetic fields? High magnetic fields are produced by electrical current, especially under load and in close proximity. To me, one of the most places we find it the most is miswiring in buildings. Okay, when source and return conductors are physically separated. So this is a great little book, Tracing EMFs in Building Wiring and Grounding by Carl Riley. This literally will go through and show you how to go through it and debug and finding the source of the problem and fixing it. What you find is that if you are following modern National Electric Code, and I brought one of my old copies. This is one of my old copies from 1987. Okay, the newer versions have made a lot of improvements. If you're following the National Electric Code properly, it will short circuit a lot of these problems. Pun intended. Okay, so what I would say is that I've found major wiring problems by going through and measuring certain things. I mean, like, why in the world am I getting this huge magnetic field? One of the things is that if you have, let's say you're running a load, okay, like a light, and the current is going up and then through the light and coming back, if the source conductor and the return conductor are very close together, the magnetic field will be tightly coupled around those two. And so you're going to find if you put the B field meter right up against it, you're going to read that B, but move away, it's going to drop off very quickly. On the other hand, if you have a miswired three-way switch or two-way switch, okay, there are ways you can miswire it so that when you turn the light on, that the power is coming from that switch, going up overhead, hitting the light, and then the return current is going through the other side, through the other switch and back to the panel. What you've just done is, what have you done with those two conductors? You've done like this. And what you've done is, you now have this big magnetic field between those conductors, okay? So, if I walk into a room with this meter right here, which is a B field meter, and turn it on, and all of a sudden it's like, oh, look at that. And it's like, is there a three-way switch in this room? They're like, well, yeah, right over there. It's like, let's go take a look. And you open it up. It's like, yep, that's miswired. It's not wired per electric code. Let's fix that wiring. You fix the wiring, and all of a sudden the magnetic field goes way down. Okay, so miswiring is really is a big one, and there's a lot of little subtle things. I'll just leave it to you. If you're in the electrical side, you can get a book like this, and it will go through, and it'll show you what not to do in detail, because there's a lot of little, like even how you pigtail circuits and so forth, ends up being pretty important. While I'm at it, by the way, this is a famous book on the whole topic, Invisible Rainbow, right? The Electromagnetic Fields, Consumer's Guide to Issues and Protection. That's another one that's kind of interesting. This book is on earthing, which I won't get into today, but it's on what happens when you ground human beings and so forth. There's a whole lot on that that's quite interesting. Another thing for a long time it was called pseudoscience, that there's now more science on, where they're able to show that if you have somebody who's been chronically ungrounded and they have inflammation in the body, that for certain kinds of inflammation, if you ground the person, that it will reduce inflammation quickly.
So things like those grounding blankets.
You have to be careful with those, because in a lot of cases with those, what they'll want you to do is plug into the ground on a power receptacle. And the whole problem is those can be very noisy. And so you can actually couple electrical noise back into yourself with those. So if you want one of those, then make certain it's being connected to a dedicated wire to a dedicated grounding rod outside where you don't have the noise. Okay? So I'm very careful about how we ground these days, right? This one's kind of controversial. This was Dr. Mercola's book on the whole topic. Here's another one that's got some interesting stuff on it. And again, for all of you electrical geeks, this one is and all of your ham radio operators, this one is like the Bible of grounding systems, okay? Because grounding is actually pretty complex if you get into it, right? So it's a whole book on grounding and bonding. So all of us engineers can geek out over.
Please do.
Yes.
Encourage.
Is that earth ground or return ground? What? Yeah. Oh, okay. Right. Yes. Yes.
Is that grounding and bonding?
Yes.
Is that for a regular person or just for electrical engineers building buildings, or is that?
The one on grounding and bonding it's practical for electricians. It's mostly aimed at electricians that are working electricians that are putting in grounding and bonding systems for all kinds of cases in buildings and in radio transmitters and in, power stations and all that kind of stuff. That's what that book is for. Okay. So, yes.
What about the shoes that are like supposed to be earthing or grounding shoes?
The one, if they actually do create good electrical contact, then they will ground you to whatever's under your feet. Now that's saying a thing, because like right now we're on concrete, and this concrete is not very well grounded because of the way the building is built. If you're outside on grass, then yes, it should work. If you're on concrete and gravel, maybe not so much. If you're on raw earth, but in other words, they're going to electrically connect you to what's under your feet. So if you're always staying inside buildings up off the ground, then they're going to just electrically connect you to the floor of the building. That's it, right? They don't magically connect you all the way to good earth ground. They just connect you to whatever's under your feet. Yes.
So we have charges that build up on us.
Yes.
Is that right?
Yes.
And then the grounding, releases it, right? And so what kind of period is it advisable, to reset or whatever?
In the ideal world, we would be continually earth grounded.
Well, let's say I'm in
If you think about it, that's what our ancestors had, right? They were barefoot on the earth all the time. Or they were hiding, or maybe they were sleeping on the ground, right? So, yeah, our body sort of is developed for that, and all of a sudden we've put our bodies into an electrically isolated condition in which we're almost never connected to the ground. All right, let's keep on going. Okay, so what else? High current wiring, appliances and devices drawing significant power, power panels, breakers, electrical service entrances, transformers, power supplies, including charging bricks, electric vehicles and charging systems, nearby power lines carrying substantial current. I didn't put on here induction stovetops. So the way an induction stovetop works is that it creates a very powerful magnetic field that couples into, that's why you have to have a ferrous magnetic pan, like cast iron or steel or something that's magnetic, because that magnetic field is time varying and it's coupled into the pan, and that literally couples energy into that material and heats it up directly. Now, power perspective, it's very efficient. As a matter of fact, if it weren't for the magnetic field exposure, an induction cooktop would be an almost ideal way of cooking, because it's very low, it's very power efficient, right? It's very responsive. In other words, you know, people like resistive electric heat's not responsive. And, you know, cooks are like, they were trying to at some of the conferences we're talking about with electrification of the buildings, they're wanting us to go away from natural gas to induction. And they come through and they brought in chefs to talk to us about how great the induction was, and they made some really compelling points. It's like one of them was like, yeah, we run these massive kitchen, and we have to keep all of the propane burners on all the time, because you don't have time to turn on and off the propane burners, because you're just going like this. So they just leave all, I don't know if you've been back in these commercial kitchens, right? It's like all the propane burners are going, okay? Fryolators, they're all going. How hot do you think it gets in these kitchens?
Well, in the Navy, we were getting up to 130, 140 degrees.
Yeah. In commercial kitchens, it's not unusual for people to be in 95 to 100 to 102 degree heat in the kitchen, right? So all of a sudden, some of these chefs had gone in and taken out all the natural, and by the way, those natural gas, they do create a lot of particulate matter, okay? So you have to have really active fume hoods so that you're not breathing in really nasty stuff. Okay, so you go in with the induction and all of a sudden, all that heat. The heat's right there and it goes right into the food. And so all of a sudden, they're like, oh my God, it's not 102 degrees in my kitchen anymore. It's like 75 degrees when we're in here cooking. This is nice. And I was like, I agree with everything you said, but what about B field exposure, right? Because I have taken my meters and measured them, and it's like, it's really high. So can you do anything with equipment manufacturers to try to better couple this and contain it so that the user isn't being exposed to that really intense B field? And we're poking them right now, trying to get them to react to that, right? But it's like, just be aware that the one downside to an induction cooktop is everyone I've worked with so far has substantial magnetic field exposure because of that. That's a good question. It's like, I think we could get it a lot better. I think it's going to be really hard to get it perfect because of the way that the pan moves around, and it's like, I think we could probably significantly increase it.
Such a thing as something that could absorb it, like a device next to it.
That's hard.
Like an apron.
Like an apron, it's harder.
Lead aprons.
Yeah, lead apron so you can cook. What I do know is like one of the, it is possible to, I know it's possible to decrease it because one of the ones we tested was one of the little 110 volt plug-in units.
They're used by caterers a lot.
Yes, they're used by caterers. And we started measuring it. Michael's very sensitive to this stuff. And he approached the front of the unit. He's like, oh, hell no. Right? So I brought the thing in, and it was like, it was way more intense from the front than the side. There was one side that was significantly lower. So literally, if he was going to cook with the thing, we turn it sideways and cook from the side, and then only just reach over and turn the controls like this, right? So it's like, yeah, somehow or another, the way the unit was constructed, that one side had a significantly, so it's like, hey, if they had just been thoughtful in the design of this and had considered magnetic field exposure, they probably could have made the unit a lot better. Yes.
One good thing about them too, though, it reduces cook time a lot
Yes.
of times, sauteing and stuff like that. So.
Yeah. I mean, they're great except for the B field exposure. It's like if we could solve that, I could fully be on board with it. Yes.
So when you were talking about the three-way switch example, one of the reasons that the pair was lower B field noise was because they were paired, right? Is there
Yes.
a possibility of having like a counter field, to sort of get back to Jake's point? Might that work?
Good question. We have to think about that. And do you still have scalar fields? It's a really interesting question.
How noisy is it? So sorry.
Oh, you mean like the induction?
Well, right. So
Yeah, the inductions are noisy. I mean, they're pretty powerful. I mean, we were seeing like in some cases like 20, 30 microgauss at the place where the chef would be sitting. It falls off by the square rule, basically.
Same. Okay.
Yeah. Okay, I need to keep on going forward. Okay. Top sources of high RF exposure. I'm just getting warmed up. RF exposure primarily comes from wireless communication systems that transmit signals through space, mobile phones, tablets, Wi-Fi routers, Bluetooth, cell phones, smart readers, wireless enabled, all that sort of stuff. You know what that is. Sources of dirty electricity. Okay. This is where you're getting noisy harmonics on top of the power running through your house. Okay. Which I put dirty electricity in quotes because when we talk technically, we can't use that term. It's conducted electrical noise is the more technical term. Okay, refers to high frequency voltage transients and noise presence on electrical wiring. It can come from switching power supplies, dimmers, electronic lighting systems, solar inverters, battery systems, variable speed motors, computers, TVs, other digital electronics, poorly grounding, wiring errors, shared neutrals. Okay, what we need to measure. What do we need to actually measure? We need to measure magnetic field, electric field, RF field strength, induced body voltage, and conducted electrical noise. Those are the dimensions that, in doing all the research, I've come to the conclusion if we measure those dimensions, those are the ones that are going to help us control the RF environment and EMF environment to keep it healthy. Yes?
New construction, how would you approach reducing the exposure?
So that's in the biocompatible design center. We're going to get to that in just a sec. We're heading that direction, right? Okay. Because that's a whole, that's a multi-day class, really.
Yeah.
Right? Okay. So, here, let me do this. All right. Here you go. Here's the table. This is table 13-4 from the biocompatible design standard. And you can see here, this is table part A. There's a part B we're going to see in a minute. These are the ones where we're doing ambient electromagnetic field conditions. We want to measure magnetic field, which is mostly coming from 50, 60 hertz power plus harmonics. We're going to measure RMS in milligauss in a time-weighted ambient exposure. Our target is less than 0.2 milligauss. The preferred range is between 0.2 and 0.5 milligauss. We want to avoid anything over 1 milligauss. Okay? So this is and I don't have a lot of time to go through all these measurements, but this is a milligauss meter. And the thing about the milligauss meter is it's measuring basically time-varying magnetic fields. So if you got it away from all time-varying magnetic fields and put it really still, it would go to 0. But it's still in a magnetic field, which is the Earth's magnetic field. The reason I point that out is because when you move this around, what are you doing? You're traveling through the field, right? So the meter doesn't know the difference between the field moving past it or it moving through a field. So when you wave it around, you'll see it spike because what I'm doing is I'm moving it through the Earth's magnetic field. When you're using a meter like this one, you have to bring it to where you want to measure and hold it still for several seconds to let that transient settle out and then get a value. Standing right where I am at the moment, I'm at 0.08 milligauss, where I am right now. So 0.08, are we less than 0.2? Yes, we're good. Now I could move around and we would find, for example, if I come over here, yeah, right? This guy, when I was over high, right here is measuring about 1.4 milligauss, okay? So that's actually putting out a field. Now I could go around here and I could show you a lot of, we could go around and look. What was interesting is like the lights are not too bad. I'm getting down to about 0.15 there, okay? So it's giving me a little bit, but it's not too bad. But we could go around and we could find all of our hot spots. We could, and especially with this one, we can find those three-way switches and other kinds of switches that are miswired, okay? Next thing we want to measure is our electric field. This is in volts per meter, okay? It's electric field in volts per meter. And this little guy right here will measure that. If I come in here, so volts per meter, you'll love this one. Okay, see this extension cord right here? Okay, it's carrying. I don't know what's connected to it.
I don't know.
Everybody see that?
Yeah.
What's happening?
It's going way up.
It's pegging, right? Yeah. So what's happening here is we're getting when you're close to this particular extension cord with whatever's going across it right now, it's like it's producing a really very intense electric field close to it. Okay. So. Yeah. By the way, that box back there behind Kelly, that's like that one's got a good magnetic field going on to it. So yeah. Right. Okay.
That suggested potentially, I know there's a lot of things, but like a mismatch between conductors where one's conducting better than the other.
It's possible. It's like that's really high.
I don't even know if it's plugged into anything on here.
Okay.
That's the funny part.
Yeah. So it's like I don't know, but that's really high. So I would want to check that out. Right? It would tell me, hey, that's pretty high. Yeah. So that's electric field. Now this thing will also do RF fields, but only up to 2.5 gigahertz. I don't have a meter with me today that actually is doing what we want it to do. There's something. The new meters to measure RF today are very specific. You need a meter that goes up to 8 gigahertz today because of all the signals up to that range. And here's the thing. This is an analog meter, which means that even if you put this next to modern digital equipment that's transmitting, you won't see it. Why is that?
It has to have its own magnetic field to deflect the needle.
What's happening is that most modern communications equipment are digital and they're sending pulses. Bloop, 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 bloop. Okay, so you get this intense bloop, and then you get nothing. And so the analog meter can't respond that fast. It literally doesn't move the needle fast enough, right? So you can't see those peaks. So all of the modern ones that will show you RF are digital meters that will actually measure the peak and show you what the peak is. Okay, that's why it says we want RF pulse modulated. We want that in microwatts per square meter, right? And here's our target and thresholds and so forth. We want to avoid anything over 1,000 microwatts per square meter. Okay, and here are the design implications. It's telling us if we're in a building or mobile or we have a device like a cell phone, what as designers we have to do to hit those levels. Okay, so that's all of that. Now there's two other things we need to measure. One of them is electric field coupling by measuring induced body voltage. And this one's the one that gets really personal. So, Opal, you want to be our so forth.
You want my shoes on or off?
Start off with the shoes on. Let's just see what that does. Okay. So what I've done is there is a 10 gauge green wire running across the floor. If you follow it that way, you're going to go out and you're going to find that there is a grounding rod that is driven into the ground out there. And the other end of this wire is connected to the ground out there. So that lets me get a ground reference point brought in here. I'm not going to try to use something from like a wall outlet. Those are it's about 2 feet in right now. Okay, so this is just a temporary ground to get me a ground reference point. So the other end is a piece of copper, And what we do is we have a person hold on to that with a good grip so that we can measure the induced AC voltage on the skin by taking a multimeter. This is a fluke multimeter. Okay, make certain we have good connectivity. Okay, good. And what we do is, I mean, I'm going to have to, this is new, I just put this one together. I'm actually going to like get a spare pair of leads and solder all this up so it's really good connection. But we take and we put the meter onto AC voltage, okay? Okay, come on. What are you doing? Let's make certain we got good connectivity everywhere. We're reading about 120 millivolts. Let me make certain this is good connection here. Sure. Good. Okay. Yeah, we're reading
Between 90 and 120, it keeps jumping.
Yeah, between 90 and 120 millivolts. What do we want? Here, we want avoid over 100 millivolts. That's bad. Okay, we'd really like to be between 10 and 30 millivolts. So she's jumping above the bad location, right? Now take your shoes off and let's see if that takes it down. Oh, immediately we go down. And where are we now?
We're about 60.
60 millivolts.
An hour ago, it was 50.
Yeah. Okay.
You're powering up. More people, more problems.
My hydration status.
Right. Yeah, humidity and connectivity, so forth. So this is literally looking at, you know, the voltage between the surface of her skin and the ground outside. That's what we're literally looking at. Yes. It's a skinning effect. Yeah, it's why it's it will go into the body somewhat, but how deep will depend upon the frequency. The lower deep it will go, the higher the frequency, a bit more of a skin effect it will go. But usually, when you're in a building like this, what you're seeing is it's harmonics from the power in the building, and so it's usually a harmonic of 60 hertz because we're in the U.S. where it's 60 hertz or 120 or 240 or whatever, right? So that's usually what that is. And so this whole thing is just literally, this is a fluke multimeter. This lead is just literally come up through here, connected to this brass coupling to a piece of copper rod. And the other end is just out. You can follow it around, you'll see it, and it's just, that's all there is to it, yes.
Where are these tables found again?
These tables are my tables from the Biocompatible Design Standard.
That's not
Published yet, but it's coming.
Yeah.
And how is your PowerPoint going to be available to these guys in a PDF? Or do you need to wait till it comes out?
If they're not place, I can probably share it with just this group.
Okay.
Yeah. Okay.
That will happen after this event.
Yeah.
Okay. And after my rest after this event.
Yes. Very good. Thanks.
How interesting that would come out of looking at that on the scope.
Yes. Now, when we do dirty electricity measurements, I don't have one of those meters with me. The most accurate way to do dirty electricity is to look at it on a scope. Okay, for everybody else, an oscilloscope. But there are meters specifically that you plug into wall outlets, and they will give you a measurement in our last thing, which is conductor electrical noise, which is our dirty electricity, right? That is high frequency voltage transients on building wiring. We are going to measure it for these purposes in millivolts peak to peak, because it's transient, right? So what we're looking at is we're looking at the transient and how big that transient is peak to peak, right? And so the meters that we are going to get are going to sample, they're going to watch, they're going to see what the spikes, and they're going to give us the maximum peak to peak voltage in millivolts. We want really to be below 10 millivolts ripple. We want to avoid anything over 50 millivolts peak to peak, right? And so forth. Those are the 5 things you really want to measure in an EMF environment to make certain you're able to track the EMF environment as humans and other beings, okay? So those are the 2 tables that I have created so far for the biocompatible design standard. So yes, hopefully within a few months, we will have the full biocompatible design standard out, and it'll have all kinds of crazy technical information like this. Plus, when we, like I didn't even pull out, like there's all of this comes all from Principle 13, right? And there's all kinds of stuff about full spectrum solar. There's like electromagnetic. There's sound. There's light environment and the amount of and circadian rhythm, circadian lighting, and and biocompatible materials, and like the standard is really pretty. Like nobody else has done anything like it I've seen that integrates the whole realm of biocompatible design into one coherent standard.
Do you think you're going to be considered like a rogue scientist or a hero in this world?
What I would say is this. One of the reasons it's taking me so long to bring it out is that every objective has its own bibliography of peer-reviewed science. So what we're trying to do is put it out, and literally it's like here, like you saw when I had an objective and had a guidelines, it's like, and here's the bibliography of peer-reviewed science that backs this all up, right? I didn't just make all this up off of, because I thought this would be clever. It's like, so what I'm hoping is that we're going to release it as a pilot specification. We're going to get a lot of feedback. We're going to see where there's pushback and where there's acceptance. We're going to take all that into account and then eventually release the 1.0 full standard. And we're hoping that as we continue going forward, we'll get better references to peer-reviewed science, more peer-reviewed science, people helping share, and so forth. I could literally keep a dozen grad students busy with what I'm doing, right?
Is the time horizon for version 1.0, let's say, by the end of this year?
I would hope that we'll have 1.0 out within the year. Yeah. But like I said, part of it is like I don't have to wrap up, but like part of it's I'm having to like do this with my team right now, and I'm send me grad students that I can right or get somebody to send me some funding so I can hire some grad students to help me with all this research, because you don't even want to know how much research goes into, like you just seen a couple of the tables from the standard, right?
Be electrical engineering grad students?
No, I need biologists and like ecologists and cultural anthropologists and physicists and biologists.
One of each, please.
One of all.
All the ologists.
Yeah. And I could use a PhD in mechanical statistics and thermodynamics if you have one. That's for the other book. All right. So I think that was what I had. Yes. So we're going to wrap up I guess we're lunching it now.
It's lunch now.
Okay. So I know some people have asked me, we do not have the Institute's newsletter started yet, but we're going to. If you're interested in being on our newsletter when it comes out, then you can scan that QR code. It should take you to our website. And then on the website, you should find the magic for subscribe to our mailing list. And then we should be, because I know people are going to ask me, right? So everybody tell me, this is the first time I've used these particular slides. Everybody tell me if the QR code works and gets you somewhere.
Yes.
Is I2RD your website?
Yes, i2rd.co should be where it takes you. Okay?
It's trying.
Somebody put that on the Telegram, please.
You got it. You got it.
Got it. Yay.
Oh, we just put the link.
Oh, is that to my bio?
Yep.
Yeah, okay, it just goes to my bio. Okay. Very good. So it gets you to my bio, but that bio is on my website. So if you just pounce around on that website, you'll find where to sign up link and everything. Yeah. Okay. So that's got us that for today. And remember, we'll come back after lunch to do Sander's stuff. And then we can ask Sander all about microbiomes and so forth, because that's what he's doing.
That's what he's doing.
Yeah. Take it away.
The best job.
Yep.
Thank you, Alan.
Yep.
Sandor Katz is the wild fermentation guy. All right, guys, it's lunchtime down there, and then we're back here, I think, at 1:30 with Sander.
Be upstairs.
Upstairs. Oh, yeah. So that's the standing class, but you really need a chair right now because
How do we get there from here? Do we go?
you can go up the stairs out there.
Okay.
That's the best way. those ground stairs. Yep. Then you don't fall down these stairs.
Yes, ma'am. That's
So I don't really use them anymore. I just happen to have this one, and because of the electric meter I bought.